All right, well, we are set to go over 7.6, looking at the double angle formulas, mainly for sine, cosine, and tangent. Okay, so the formulas are a little unique in that it's going to tell us like what to do if there's a coefficient or a number in front of the theta. So we saw what to do when we were solving equations, but now let's look at it when you're just trying to prove identities. So sine of 2 theta is going to equal 2 sine theta cosine theta. And it's important to remember that the identities work in both directions. So 2 sine theta cosine theta, you can switch that back to right into sine of 2 theta. Now tangent of 2 theta, that's the next one down in your notes. That one's going to be 2 tangent theta all over 1 minus tangent squared theta. And then cosine of 2 theta, this one's the fun one because cosine of 2 theta has 3 different options, and that's because of the Pythagorean identity. So the first one that we can use is cosine squared minus sine squared. So we can use that Pythagorean identity and we could adjust it slightly. We could take the cosine squared out and get it in terms of sine. You can take the sine squared out and get it in terms of cosine. So the other alternate forms would be 2 cosine squared minus 1 and 1 minus 2 sine squared. When you go to prove identities, it doesn't really matter which one of the 3 you actually choose. One of them, though, will definitely be faster than the other 2, but they will all work. They will all get you there. So if you don't know which one to pick, just pick one and go for it. Okay, so let's start out with example 1. So we're just going to evaluate given some known quantities. So sine of 2a. So what you're given is only in terms of a. It's not given in terms of 2a. So we have to adjust this and apply that double angle formula on it. So 2 sine A cosine A. So we can use what they gave us. So we know that sine of A is equal to -4/5. But the cosine of A we don't have. But we can use the other information to find it. So sine of A was -4/5. And the A itself is between -pi/2 and 0. So that's going to restrict us to quadrant 4. And you can draw a triangle. And then the 4/5 you can use to label your triangle. And now you've got a 3, 4, 5 triangle, so this is a 3. So cosine of A, just do cosine of this triangle, and it would be 3/5. And then just multiply everything together to give you a -24/25. So part B would be pretty much the same idea. So I'll let you guys look at that on your own. So let's look at example 2. So find the exact value of cosine of 2 times the inverse tangent of -4/3. If we had a really good way to evaluate inverse tangent of -4/3, then this wouldn't be too bad because we could evaluate this, multiply by 2, and then do cosine of the resulting angle. But this isn't going to give us an angle that we can do by hand. So we can't just evaluate it and then keep going. So we've got to apply that double angle formula to it. because you really have one. You've got a 2 here, so anytime this is an even number, you can use that double angle identity. And again, it's not going to matter which one you pick. You just got to choose one and go for it. So let's use that second one. And just because the second and the third, they only have one trig function in them, whereas the first one has 2. So this right here, this inverse tangent of -4/3, that whole thing is acting like your theta. So when we do the formula out, it's 2 cosine squared minus 1, and we have to fill in the angle here. So what you put in there is your theta. Well, what's acting as the theta? Well, the inverse tangent. So it becomes this. And remember, when you raise a trig function to a power, that means you're raising the entire thing. So another way to write it would be like this. So 2 times cosine of inverse tangent of -4/3, and then the whole thing is being squared, and then minus 1. So let's evaluate the cosine of the inverse tangent. So that's going to require a triangle. And the tangent, or inverse tangent, since it's negative, that means you're going to stick it in quadrant 4. So opposite over adjacent. So opposite over adjacent, so you have another 3, 4, 5 triangle. And now you can do cosine of this triangle that we drew. We don't care what the angle is. You don't need this. You've got all the sides. So cosine of this triangle would be 3/5. And then don't forget, you're still having to square it. And then just keep going. So square the 3/5. 9 over 25. Times it by 2. (18 over 25), and then minus 1. So -7 over 25. Okay, let's go ahead and verify an identity in the next example. And they're all going to utilize one of those double angle identities. Somewhere in there you're going to use one. Mainly because that's the section we're in. Okay, so let's go straight to example C. That was probably the most challenging out of the group. Mainly because the angle in there on the left side is odd instead of even. So surprisingly, that's the side we're going to choose. Because I don't really have an identity that's a real good one, or I can't really use a double angle identity in a really good way. If I did, I'd end up with some sort of a fraction in there, which really is not all that helpful or all that fun. So anytime your angle is odd, what you are going to do is you're going to write it as a sum. So you're going to find, two things that would add up to that 3 theta, or sometimes would subtract down to the 3 theta. Just try to be nice to yourself and choose the smallest numbers possible. So that would be 2 and 1 for this. And now that you've written it as a sum, now you can apply that sum formula from the previous section in 7.5. So this is like the A, this is like the B. So sine 2 theta, cosine theta. plus sine theta cosine 2 theta. And we got to keep going, because if you look at your answer and where you're trying to get to, the angle in there is just a theta. There's no 2 in front of it. So that means I have to adjust this term, and then I have to adjust this term. So sine of 2 theta, there's only one option. It's just 2 sine theta cosine theta. And this cosine of theta is still in there. So plus is plus. We'll leave the sine of theta, and then move on to the cosine of 2 theta. So now you've got that option again. You can choose any of the 3, but one of them is going to be faster than the others. So to tell, look at your answer and where you're trying to get to. The answer we want just has all signs in it. So let's choose the option that just has all signs in it. So 1 minus 2 sine squared. Again, if you chose a different one, it's totally fine. It'll work. You're just throwing in like maybe another step. Okay, so let's play with what we have. So here, I can multiply the cosines together to make a cosine squared. And on this one, let's distribute the sine. So I end up with that. So I'm getting closer to what I want, because now I've got a power of 3 somewhere in the expression. That's where I'm trying to get to. So the only thing that I really have left to take care of is this big old cosine squared. I don't want cosine in there at all. So I need to replace it with something. And I can replace it with that Pythagorean identity again. And then I can distribute, I can do the algebra. And then just combine your like terms. So 3 sine theta minus 4 sine to the third, which is what we wanted to get. All right, go ahead and turn it over to the next page, on page 9. And I'll show you how you can use those double angles, those double angle formulas, more than once. Because every time there's an even number in front of the theta, you can keep applying that double angle formula as often as you need to. So let's go with the right-hand side. So you're starting with that sine of 4 theta. So that's going to become, like, I can use that double angle formula with sine. So the formula says 2 sine and cosine of whatever angle I started with. And what people want to do, and where the confusion kind of goes, is they assume that whatever number's in here is the same number on the outside. That's not the case. The formula says this: sine of 2 theta is equal to 2 sine theta cosine theta. So it's an established formula, so any numbers in there are kind of fixed. So if a formula starts out as a 2, then you're always going to put a 2. Like, don't change it to a 4 just because that's a different number. you're still just trying to apply the formula. So it's 2, and then the angle gets cut in half, and it goes right into sine and cosine. So if you cut a 4 theta right in half, that's a 2 theta and a 2 theta. Well, now you can use a double angle formula on each of those. So sine of 2 theta, we just wrote it. 2 sine theta cosine theta. And then cosine of 2 theta, the one we want to choose is the one that's actually written out in the problem. 1 minus 2 sine squared. So we're nearly there. Forgot where we're trying to get to. Just multiply the 2 and the 2. There you go. Okay, and I'll let you guys look at example B on your own. So moving to example 7, let's do the second example in there, part B. So solve the equation of sine of 2x is equal to cosine of x. So it's really annoying, whoops, if you're trying to solve a trig equation and you have more than one type of trig function. It's especially annoying when the angles don't even match. So when the angles don't match, you gotta get them to match. So that's applying any formula you can think of so that all the angles are x's or all the angles are thetas. So with sine of 2x, we're gonna apply that formula again into 2 sine x cosine x, and the right side we'll just leave it the same. So now I'm going to set it equal to 0. And I can factor out a cosine of x. So cosine of x will equal 0, and then sine of x will equal 1/2. So cosine is 0 at pi over 2 and 3 pi over 2. And sine, that's equal to a positive half when you're in quadrant 1 and quadrant 2. So pi over 6 and 5 pi over 6. Okay, so let me show you something that sometimes, or something that people want to do with that equation, and it's something you do not want to do. So let's take it from that step right there. 2 sine x cosine x is equal to cosine. Well, what a lot of people want to do with this, instead of moving the cosine over like we did in this case, they just want to divide it out. So they'll divide everything by cosine. And then they're left with that, and then just divide by 2. And they solve it and go, okay, x is pi over 6 and 5 pi over 6. And those are the only answers that you would get. Well, if you look, they don't get these two answers here. So you do not want to divide by a trig function if your goal is to have it just cancel out. Like if you're just trying to get rid of it, don't divide it out, because if you do, you're going to miss, you could miss a whole set of answers. So just set everything to 0 and factor it out. Don't divide it out. Now that's not to say you can't ever divide. If you had this equation, you could divide by cosine, because you wouldn't completely eliminate it from the equation. You would eliminate it from the right side, but you're not really eliminating it from the left. It's really still in there, because you can change the sine over cosine into tangent. So your cosine is still in the problem. So that's when you can divide by a trig function, when you're actually going to use an identity to still kind of keep it in there. But don't divide by it just to cancel it out. Okay, so that is the end of 7.6, and it's also the end of the chapter. So the next set of notes that we're going to see, and then I'll start posting videos for, will be for chapter 9. And we're going to get into vectors and polar coordinates and all that sort of fun stuff.